Good afternoon and welcome to the ASV's solar section meeting. Today we're going to try and have a look at the sun and have a chat about the sun, and to take us through the afternoon's events, we've got Russell Cockman, the section director for solar. We have to get him to unmute.
Here we are. So welcome everyone to this, as Marcus said, this solar section solar demonstration on behalf of the Astronomical Society of Victoria. And we do hope that we can do some solar observing today. Now, whenever we consider observing the sun, there's a very, very important warning to everyone that observing the sun can be dangerous. That's because the heat of the sun can be focused onto the retina, which will cause immediate and permanent damage to the eye. So please do not look at the sun unless you are using correctly filtered equipment over your eye or over your telescope or binoculars. That is extremely important. And hence the equipment that we are using today is properly filtered to protect the eyes, and to have it live streamed through the internet is absolutely the safest way to observe the sun of all. So thank you very, very much for joining us. Can we pass over to Anne-Marie? Hi, Anne-Marie.
Hi there, how are you?
Very well, thanks. Very well. Now, what's the weather like out your way today?
Well, we had rain about 5-10 minutes ago, so I've just set it back up again. So give me another 5 before it'll be warm enough.
Okie dokie, that's wonderful, wonderful. So any other bright ideas about what we can do until then? Now, Anne-Marie, do you have any? You mentioned that you might have had some videos pre-recorded. Have you got any of those for us?
So I've got an image that I took earlier today. Let me just find it. Sorry, take me a bit.
No worries.
I was hoping I'd be up and ready, but the rain put me off.
Understood, and it has come along at exactly the wrong time.
Yeah. All right, now I've just got to figure out how to share the screen.
Down the bottom.
Yeah. Share screen. Goodness, I've got so many screens open. Must be that one. There you go. That's one I took earlier today.
Wow.
Can you see that?
Wow, that is spectacular.
Just give me a minute and I'll see what I've got open at the moment.
So, Russell, what are we looking at here at the moment? The lovely little black spots in the middle there.
So, ladies and gentlemen, this is the sun imaged in the special light of hydrogen, which is a beautiful, rich red color. And looking at the sun in this light of hydrogen, which we call hydrogen alpha, if we could see it up again, Anne-Marie, it's...
Oh, is it going? Sorry, you following my screen, are you?
We are, yes.
Sorry.
No worries.
How do I just make it that screen, Mark?
You have to go share screen and then choose the window that you want to share.
Okay.
It's all
and
good.
I have to stay on that, do I?
Yes, you will. Yeah.
Sorry. There you go.
What a gorgeous image, Anne-Marie. Well done.
Thank you.
So this is the sun taken in the red light of hydrogen, so-called hydrogen alpha. And what we see here, can you see my... I don't know if you see...
No, you won't be able to see your pointer.
So, Anne-Marie, could you use your pointer? Yes. So here we are looking at a couple of sunspots, so-called active regions on the sun. And look at that all the wonderful structures that we see on the sun. They are actual features on the sun. And to put the sunspots into perspective, the sunspots, although they appear darker than the surrounding brighter sun, they're only a couple of hundred degrees cooler, about 5,200 degrees Celsius, which is very, very hot by human standards. But yes, about 5,200 degrees. Because of the contrast, they appear dark. But all those structures you see there, ladies and gentlemen, are actual structures on the sun, and you can see these structures with your own eyes through a telescope equipped with hydrogen alpha viewing. Absolutely beautiful. And over towards the left of that sunspot pair, there's what we would call is a filament. So if anyone can recall seeing a picture or having seen the sun in hydrogen alpha, you will have seen these prominences, these so-called, flames of red light licking off the edges of the sun. And so these objects, which we call filaments, are prominences that are seen silhouetted against the slightly brighter and slightly hotter disk of the sun. Now, this particular layer of the sun we are looking at, and we can consider the sun a little bit like an onion. So that brilliant sun that we see shining in the daytime, that light is coming from a region of the sun which is called the photosphere. But a hydrogen alpha telescope actually looks a little bit above the photosphere to a layer which is called the chromosphere, which is the red region characterized by its emission of red hydrogen alpha light. So we're actually seeing a region slightly above the brilliant, dazzling photosphere that shines for us. And so we are seeing all these beautiful structures in the photosphere of the sun. Now, ladies and gentlemen, if you don't have a solar telescope, the only time you can see the photosphere with your own eyes and safely is during the brief few seconds during a total solar eclipse, when the moon does the job of hiding the dangerous, dazzlingly bright photosphere, and just around the edge of the moon, before the sun is completely and utterly, totally eclipsed, there's this little red line is visible for a few seconds, which is the photosphere. So I'm just trying to point out that solar eclipses can't be dialed up anytime we like. We have to travel the world to see them, roughly every 18 months. But observing the sun through a hydrogen alpha telescope is a rare view, because it means we can observe the beautiful photosphere of the sun anytime we like and not have to wait for a total solar eclipse for that. Fantastic.
Now, Russ,
Yes.
Brenton's put in the chat screen saying that while we're waiting for Anne-Marie's and Lee's solar stream to get kicking in, to update us with what the solar cycle is.
Well, that's very, very good. Thanks for the question, Brenton. It's in my understanding, a picture is worth 1,000 words, and I do have a presentation on the solar cycle, and I can look up. I'll just oops. You cannot minimize Zoom whilst you're recording this meeting. That is good, right? So I actually have a presentation on the solar cycle, and I'll just show a little bit of that presentation to highlight what the solar cycle is all about. With the meeting's agreement, of course.
I don't think anyone's going to complain, are they? So, I think you're right to go, Russ.
Okay, just loading up the presentation.
So while you're loading,
Yep.
we have a question from Kevin, who's watching a stream and wants to know how big the sunspots are relative to the size of the Earth. Those ones we just looked at.
Thanks, Kevin. And I was going to get onto that. I do apologise, but I got a bit sidetracked.
Sorry.
But thank you very, very much for that question, Kevin. It's a beauty. My estimation is that those sunspots, the Earth could fit inside those sunspots easily with room to spare. Okay, if we see a view of the entire solar disk, 109 Earths will fit across that solar disk, to give you an idea of just how big the sun is. So I would say that the Earth would fit inside those sunspots, perhaps even 2 Earths, with room to spare, just to give you an idea of how large these structures actually are. Great question.
How's you going with this sharing of your presentation?
Okay, I'm just going to get into it now. And
I'm going to go share screen down the bottom.
So can you see that, solar cycles?
We certainly can, yes.
And a beautiful red sun. Well, I will start the presentation, and I'll only go through just a few slides just to review what the solar cycle is all about. So I'll start from here. So here's the full disk of the sun seen in the beautiful red light of hydrogen alpha. Now really, no picture can do justice to just how beautifully radiant this red color is. But however, here are some features that we will see on the sun, as we've seen today. Hopefully you can see my cursor moving around. Some sunspots here. The white areas near the sunspots are called active regions. So these are sites of explosions on the sun, releasing energy gazillions of times more than the energy released in an atom bomb explosion, just to give you a bit of context there. Enormous amounts of energy. Quite a few active regions, as you can see here, here and here. Here's a filament, here's another one, another filament here. And around the edge of the sun are prominences. So these are sites of explosions on the sun, where that energy basically blasts solar stuff into space. Now, this stuff that is blasted into space often doesn't last long, suspended there. It eventually falls back into the sun. But sometimes a blast can be so large that stuff is actually billions of tons of solar stuff is blasted into space to add to the solar wind that the sun is constantly emitting into space. So this was taken during a time when the sun was active. So the sun goes through times of high activity and times of low activity, and there's roughly an 11-year cycle from one period of high activity to the next period of high activity. And this is called the solar cycle. And that's me, Solar Section Director of the Astronomical Society of Victoria. So what do we mean by solar cycles? Well, if you consider that the sun is composed of plasma, which is charged particles, when charged particles move, they create magnetic fields. So the sun is just a big ball of moving plasma. So the internal bits of the sun are just huge collections of magnetic fields. And the sun is a huge magnet. So the solar cycles are actually changes in the magnetic characteristics of the sun, which rise and fall over time. And a good way to evidence this rise and fall of solar activity is by the number of sunspots that are visible from day to day on the sun, these little black spots. Because dark areas in the brilliant solar photosphere. And the number of sunspots visible rises and falls over roughly an 11-year cycle. On average, it's about 11 years, but sometimes it might be 9 years, sometimes it might be 13 years, but on average, it's about 11-year cycle. At what we would term solar maximum, there are lots of sunspots visible. Large ones, small ones, large ones with very complex structures with lots of little sunspots around them. That's indicative of a lot of stored magnetic energy. And when the magnetic energy, when the magnetic fields combine, that energy is suddenly released in an explosion, a flare, and stuff is blasted into space. Either we see it as a prominence or as an increase in the solar wind. But then we have solar minimum, where few or even no sunspots are visible from day to day on the sun's visible surface. Now, the 11-year cycle of solar activity was discovered by Samuel Schwab in, if I can get this out of the way, in 1843. So less than 200 years ago, ladies and gentlemen, this 11-year cycle of activity was actually identified.
Okay, so have we got some streams ready to go?
I'm ready.
Okay, fantastic. So
Yeah.
I
Let me
shall,
just figure out how to do it again.
I will try to exit from this because my screen seems to have frozen. Okay.
There you go. I solved it for you.
Thank you very much.
That's all right.
Fantastic.
You got that?
Yep.
Not much
Nice.
else happening on it today.
No worries, Anne-Marie.
You want me to scoot around?
Well, let's just continue to have a look at that whilst we talk about it. Okay, so and is this the video of the sun that from which you?
No, this is live.
This is live. Oh,
Yep.
even better. Fantastic. So, ladies and gentlemen, this is live streaming of the sun as we see it. Well, in fact, it's 8.5 minutes ago because that's how long it takes light to get to us from the sun. 8.5 minutes. So, Anne-Marie, if you wouldn't mind just pointing your cursor at, yep, so there we are. There's a sunspot, another sunspot there. Between those two sunspots is a lighter area. So these are the sites of relatively minor explosions on the sun, releases of relatively small amounts of energy. But to the upper left of that sunspot there's a lighter area. So that is a region of solar activity, of explosions on the sun, of what we would say flaring. And there are ways of characterizing the strength of flares, and that's based on the X-ray, the intensity of X-rays coming from these flaring regions as measured by probes orbiting the sun. Okay, fantastic. Also, ladies and gentlemen, have a look at the sun is not smooth by any means, is it? It's quite blotchy. You've got darker patches and you've got lighter patches. So this is actual structure on the sun's chromosphere. How beautiful is that? And you'll see when the video is running that the sun is sort of boiling a little bit. That's not an effect of the sun. That is simply an effect of looking through the Earth's atmosphere, which is causing the sun to appear to be boiling a little bit. However, that's not to say that these structures on the sun are permanent, because if we could observe the sun for an hour or two, we would see actual changes in these smaller structures on the sun, which are true changes in the appearance of the sun.
Now, Russell,
Yes.
we've got a question from Kevin, who's in our Zoom stream at the moment. He wants to know what filter Anne-Marie is using at the moment.
Well, Anne-Marie, you can please tell us that.
I'm using a Daystar quark filter, which is a H alpha, and it also incorporates a Barlow in there as well.
So, just a brief description on how your equipment is set up, Anne-Marie.
Well, I'm running on a Skywatcher HEQ5, and I've got my ED80 refractor on top, so and then the Daystar quark filter on that.
So that's an 80mm refractor, a telescope that's got lenses up the front.
Yep.
And it's on a mount which, I mean, that sun looks pretty stable in the field of view. So your mount is polar aligned to south, is it?
Semi.
Semi. That's all right. No, that's good. So your equipment is reasonably well set up in order to track the sun as the Earth rotates. Yeah, very, very good.
And little clouds going across now.
No worries, and that's good to know.
Just see them popping across.
Yeah.
Now, Russell.
So one last thing for Anne-Marie. Not many people know what the Daystar quark is. So does it? Where does it go on your telescope? And
can I show you a photo? It's probably easier to explain.
Yes, that'd be
Sorry,
great.
I'll just stop sharing for a sec.
It's very, very good if people can actually see what.
I can stop sharing for you if you want.
Yeah, thanks. That's all right, I got it. Okay, I'll just see if I can find a photo.
While you're looking, we had a question from Rachel Russell, who wanted to know, did you say the dark patches were like beaches, the dark patches on the sun, when you were giving your explanation before?
Hi, Rachel. Thanks for that question. Much appreciated. So those dark features.
Features. There you go. Features.
Yes, so they are structures on the sun, which are of the sun, not of a cloud in our Earth's atmosphere or something in space getting in the way of the sun, sort of thing. So they're actual structures parts of the sun that we can see when we observe the sun. So everything that we see today, apart from those clouds that we're passing through, which were Earth-based clouds, everything we see today is actually on the sun, our very own star, about 150 million kilometers away from us. I hope that answers your question.
Anne-Marie, did you have the photo to share ready?
I can't find it. No, it's in a presentation I did, and I did remove it the other day, and I can't remember where I put it.
Yeah, that one amongst the members, and maybe put a post on the social media.
Yeah. But to explain, I don't know if you can see me there.
Yep, we can.
Move back. So on the end of the refractor, it's a filter. It's about that long, and it's like just round. It just sits on the end of the filter of the telescope, and then the camera is on the end of that. And it's just a filter. I don't know what's inside it. I'm not technical that way. I just know it works.
Very nifty.
Sorry?
Very, very nifty indeed.
It is, yeah.
Now, I couldn't see what you showed because I've just gone to the internet to the Daystar site.
Yeah.
Could I show the picture that's
Sure.
on the site? Okay, so I've got to go back to Zoom and share. Ooh. Well, would you mind, Mark, putting me back?
You should be able to share. Everyone can share.
I found it. I found my photo.
Excellent. That's excellent, Anne-Marie.
Except I don't have one of the solar. I've only got one of the other. No.
Okay, well, I can share screen then because I've got it here. So can you all see that?
Yes.
So, ladies and gentlemen, this, well, as you know, a telescope needs an eyepiece in order to magnify the image that the lens or the mirror produces. And so this Daystar quark takes the place of the eyepiece. So it takes the light from your telescope, and preferably a small telescope that uses lenses rather than a telescope that uses mirrors for technical reasons. But let's just, so a telescope that uses lenses is known as a refractor. So if you've got a refracting telescope, you can put the Daystar quark where your eyepiece would go, right here, and this goes in between, and within the body of this is a little hydrogen alpha filter, which gets rid of all of the sun's light and heat, apart from a little band of red light, which corresponds to hydrogen alpha. And then you put your eyepiece here. So in other words, you can convert your refracting telescope that you'd use for observing stars and the moon and planets at night, put one of these on, and you can observe the sun during the daytime. So it is a wonderful device for being able to use your nighttime telescope for daytime use.
Yes. Russ, if you click on the little sun there.
Yes, here we go. Yes, absolutely. Yep. So I'll just do that again, folks. So if you go to the Daystar quark site and click on that icon, that shows you some professional solar telescopes around the planet, which are used to constantly monitor the sun in hydrogen alpha. And here we have one at Nearmont in Western Australia. And these pictures are updated every minute, every 2 minutes, every 5 minutes, but in other words, regularly. And this is a wonderful way. Anyway, we've just seen them update. And this is a wonderful way to see what is happening on the sun at the present time. So
there's something in there I haven't seen.
And there's the sun in hydrogen alpha, full disk of the sun, showing pretty much exactly what Anne-Marie has shown us, but the full disk of the sun. And here we have the prominences around the edge. Here we are, quite a few prominences. Because the sun activity is starting to rise towards maximum, which will occur in maybe 2024 or 2025 or thereabouts. And as the sun's activity rises towards maximum, we start to see more explosions, more sunspots, more explosions, more prominences around the edge of the sun. Absolutely beautiful. And I can actually zoom in on that. Whoa. So that's what Anne-Marie showed you earlier, through her very own telescope. The orientation would be slightly different to what we're seeing here, but the features are, remember, bearing in mind this is a professional telescope we're looking at here, ladies and gentlemen. So the features that Anne-Marie has shown us are all there. Fantastic, giving a measure of the quality of the equipment that Anne-Marie is using.
So we've got a couple of questions, Russ.
Okay.
Brenton wants to know what the difference between the chromosphere and prominence models are of this equipment.
Ah, yes. Thank you very much for that question, Brenton. There's not a lot of difference, really, to be absolutely honest with you. The main difference is that prominences tend to be a little bit fainter than the features on the solar disk themselves. And also, I mean, this is a technical answer, but the sun is actually rotating, and I can actually show you, to answer this question, I can actually show you the rotation of the sun. So I shall get out of this image, and if we click on Learmonth here, this will go into a system where it has now collected 74 images to create a video. How fantastic is that? So I'll click on play. So putting these videos together, that's cloud going across. You can see that over the period of these videos, not very long at all, there's the time scale there, about 6 hours or so. You can see how much the sun has rotated in 6 hours. So therefore, the sun is rotating, and therefore it means that there's a phenomenon called the Doppler effect. That means that a region of the sun which is rotating towards us, the hydrogen alpha wavelength of light will be slightly blue shifted, i.e. slightly lower wavelength, but the region of the sun which is rotating away from us, the hydrogen alpha light will be slightly red shifted at a slightly longer wavelength. Now, the way these hydrogen alpha telescopes are set up, they've got a very narrow bandpass. Not many nanometers of light is allowed through. So the Doppler effect can actually affect the amount of the quality of the views of the sun because of the Doppler shift. So the quark prominence is more or less set up to observe prominences on the edge, which aren't effectively moving away from us or towards us, whereas the chromosphere versions has a little bit more scope for adjusting the wavelength of the bandpass to get the best possible views of the sun. And that's my interpretation of that. And unfortunately, one has to talk a little bit technical when trying to answer questions of that sort. But thank you for that question, Brenton, and I hope that was a satisfactory answer for you.
Got a couple of other ones for you, Russ.
You
with the equipment, and this one might be for Anne-Marie.
Please do.
But with the equipment, so Lenny wants to know, with the equipment or that Anne-Marie is using, is it a digital or optical magnification when we were looking at the sun before?
No idea. Russ?
Russ might be able to answer that one.
It's an optical magnification because Anne-Marie has a video camera attached to her Daystar Quark. So that takes a video stream of the sun to her computer. So here the telescope is acting as a magnifier, increasing the size of these features on the sun. So it's an optical magnification. Now, bear in mind also that the chip that Anne-Marie is using is a relatively small chip, so that adds a little bit of magnification as well. So it's an optical magnification simply through the combination of the telescope and the chip in the video camera.
And the Barlow inside the Daystar Quark.
And of course,
which is a 4 times.
Absolutely. Thank you for that. Yep.
Yep.
Yep. So that's an optical magnification. So, ladies and gentlemen, whilst we're looking at this video of the sun, have a look at the prominences over here. You can see them changing over 6 hours. They come from nowhere, and you can see them changing in structure up here and down here. So the sun is a dynamic object, meaning that it is constantly changing. If we watch it long enough, and we're only talking about an hour or two to see changes, we can see those changes very, very clearly with our eyes. Also, I want you to notice this region here. You'll see some little white sparkles coming out. There's one. These are actual explosions on the sun, which we call flares. And as I said before, these flares have a means of measuring their activity, the amount of energy that they're giving out. But quite clearly, we are seeing some flaring activity on the sun as we watch it, at least in this video of the sun, which was only captured a few hours ago up until present.
Now, Russell, we've got another question as well. Jamie wants to know, could we see a Carrington-type event during this solar maximum?
Well, that is an excellent question, Jamie, and thank you very, very much for joining us and for that question. The short answer is, I hope not. The Carrington event occurred in 1859, and it was an extremely powerful flare or series of flares on the sun that from a sunspot which was Earth directed towards Earth. So the Earth received the full brunt of the explosion, manifest in a huge stream of solar particles as it passed by the Earth. And please, ladies and gentlemen, although the sun is 150 million kilometers from us and the solar wind, a stream of particles from the sun is constantly passing by us, that stream of particles passing by us can have visible effects on the ground. We can see those visible effects because, or to cut it short, those stream of particles passing by is actually a magnetic field that is passing by the Earth. That magnetic field interacts with the Earth's magnetic field, and that can allow those magnetic effects to be seen on the Earth through electrical conductors like telegraph wires, electrical transmission wires. These act as antennas for the energy. And in 1859, as a result of the Carrington event, wooden telegraph poles in the US were catching fire because of the enormous amount of electrical energy that was being created in the telegraph wires because what was happening several hundred kilometers up in space. Now, in our modern technology, an event similar to the Carrington event would no doubt knock out our geostationary satellites, like our GPS, our communication satellites. If we weren't quick enough, could knock out our electrical supplies here on Earth and create a lot of havoc. If you think COVID-19 has caused disruptions to the way that we have known, the way that we are used to living, imagine a life without electricity or GPS or what have you. That is the potential of a Carrington event in our modern era. And it will happen. It will happen. It could happen this solar cycle. No one can tell. But who knows? We may witness a Carrington event in our own lifetime. And just to say, to give a little bit of more backstory on this, the Earth was very lucky to just miss a Carrington type event in 2012, just 9 years ago, that the sun unleashed a massive flare, which happened to pass by Earth, but the Earth wasn't in a position to have this stream pass by. It missed us. But the belief is that if the Earth had been hit by this stream of solar particles, and really we're only a week away from that position, it could have caused an event on the Earth's surface very similar to what we saw with the Carrington event. So, as I said, the short answer is I hope not. Anyway, I hope that answers your question.
Another one from Lee wants to know, in 6 hours, how far would that prominence that we're looking at right now, how far along would it have travelled?
In kilometers?
How far around the disk? So how much further? So we see how far it travels at the moment. So in another 6 hours, how much further along would it be from where it currently is on the video we're watching loop now?
Well, even the distance.
Perhaps the best way to answer that is to say that the sun, the equator of the sun Takes about 27 days to complete one rotation. So 6 hours is a small part of a day, a quarter of a day, which is a small percentage of one solar rotation. So looking at the sun from here to there, that's 1.4 million kilometers, ladies and gentlemen, 1.4 million kilometers. So moving from here to there, it's going to be 100,000 kilometers, I reckon. About, let me think, about 7 Earth radii, something like that.
In a 6-hour period.
Anyway, I hope that answers your question,
That's
Lee.
a pretty good answer. Does Emery, have you still got some sun there? We put the live feedback on, or
No, sorry, we've got cloud.
oh, it clouded out.
Okay.
Yeah.
That's a shame.
It'll come back.
Yeah, well, thank you very, very much for showing us your live feed, and I do hope that there is a patch of blue sky coming your way, so you can show us another feed from your equipment.
I'm keeping my eye on.
Thanks very much. And it is beautiful to see the sun in real time. Fantastic.
Wondering how Lee's going. So I'll see if he's been able to.
No.
See if he's able. He said the sun is there, so I'm not sure if it means he's able to.
Not
Yet.
Not
yet. Not yet.
No, it's oh look, it's just no, it's coming out again. But I bet if we swap over, it'll be like it's in clouds for sure.
Okay, Lee. Well, please keep a heads up for us on that. Whilst we're still enjoying this animation from Learmonth in Western Australia, not far from Exmouth, actually, where there will be a total solar eclipse in April 2023. So, ladies and gentlemen, that's less than 2 years away. A total solar eclipse over Exmouth in WA in April. People often ask me, how long do prominences last? Well, I wish I had this video to show them, because you can see how quickly prominences can form and how quickly they can change shape and how quickly they can fade away. So bearing in mind, this video was taken over about 7 hours, looking at the time clock up there on the top right-hand corner of the screen. So prominences, they can last a few hours, they can last a few days. That begs the question, how long do sunspots last? Well, the sunspots can often survive a complete rotation or two of the sun. So we're talking about close to 2 months. A particularly large sunspot group can last on the sun. Other times they may only last a day or 2 days before they just, I was going to use the word evaporate away, which is not a particularly good word in this context, before they disappear.
Now, while you're having a drink there, Russ, we've got another question I'll read out. Jamie's asking a lot of questions. Yeah, no, I can see you. They can't. I can see you having a drink. Jamie's asking another one. Can you tell the difference between a prominence and a CME?
That's an excellent question, Jamie. Thanks for that. Probably yes. So these flames, for want of a better word, prominences is a better word, around the edge of the sun. These are visible indications of explosions on the sun, relatively minor explosions, because the prominences aren't particularly large. But when there is a large explosion on the sun, a large flare, that can create a huge prominence, but more likely it will create a huge ball of plasma, which will then explode into space at ridiculous speeds. I mentioned the solar wind before, so the sun is constantly emitting a stream of particles, which is called the solar wind, and typically these particles are traveling at about a speed of 400 kilometers per second, not per hour, but 400 kilometers per second. whereas the stream of particles from a CME might be traveling at 2,000 kilometers per second as a result of the energy. So prominences, CMEs are related, but it's very, very hard to see a CME in these hydrogen alpha images. And yet, remarkably, there was a total solar eclipse through Argentina last year, in December last year. And photographers who were fortunate to get there because of COVID restrictions, etc., they actually, in their photographs, they actually saw a CME during totality last year in December 2020. In their finely detailed images of the sun, they actually showed a CME bursting from the sun, and that's a pretty rare event to see a CME occur at the time of totality, which only lasted about 2 minutes and 5 seconds. But how remarkable was that? So they saw a structure coming out of the sun, which is the structure that a CME has. So how lucky were they to see that once in a lifetime event? Anyway, I hope that answers your question.
Jamie said that's amazing. Thank you, Russell. So I think you've answered both of her questions very well, which is great. I think Lee might be in a position to share his. We're going to try. So Lee's also helping us do this stream to Facebook and YouTube and to Twitch. And hello to our one Twitch follower who's watching us at the moment.
Welcome, Twitch.
A new platform that we're streaming on. So it will take a while to get the numbers up on Twitch, but we've got somebody watching at the moment. So thank you for watching.
So if you could stop sharing, Russell, and I'll share it from here.
So if this goes weird, then we'll blame Lee.
Yep. Okay, let's see if that works. No, I don't think it's going to YouTube at the moment. So
no, it's not.
Yeah. Okay. So we'll can that share. Hang on. I can't even find where.
You're getting some nice advertising, though.
Yeah. No, we don't need that. Can you cancel the share from Zoom for me?
Yes, I can.
Oh, there it is. I couldn't find the window. Okay.
We're back.
Give me a minute. I'll have to figure out how to get that.
No worries. No worries. Any more questions whilst we're waiting for Lee to?
Anyone in the room got a question? We've had a few on Facebook and YouTube.
Great questions, everyone. Great questions.
I'll ask a question if I can. Russ?
Yes, Ashley.
So you're talking about the Doppler effect of the rotating solar mass. So what's the size of the wavelength shift that you can perceive with when you obtain this?
Well, see, the hydrogen alpha telescopes like Anne-Marie's Daystar or the ASV's Lunt, they've got a very narrow bandpass around the hydrogen alpha wavelength. It's about half a nanometer.
Right.
I think perhaps even less than that. It's maybe less than 0.1 nanometers. And that narrow bandpass is required in order to get rid of the wings to improve the contrast. So that's a very narrow bandpass, and hence the Doppler effect can actually move the hydrogen alpha wavelength out of that bandpass, or at least only allow a little bit of it to sneak in. So that's why the best, and in fact, Anne-Marie has a little tuning device on her Daystar as well. We can actually tune the bandpass, move it around, so you can maximize the view of the sun by allowing the maximum amount of hydrogen alpha light that has been affected by Doppler effect through the filter and to the eye.
I see.
It is significant, yes.
Very interesting. Thank you.
So I do have another question for you, Russell, from Lenny. Any tips on using the ESA NASA app J Helio Viewer?
Oh, well, that is a wonderful app, a wonderful program on the internet. just think that to be able to utilize the images from equipment that has costed billions of dollars to put up there, and to create videos from a whole range of views of the sun at varying colors of light. That is a marvelous opportunity to do that. And Jade Helioviewer is a very straightforward way of being able to do that, to create breathtaking animations, videos of the sun in all of its dynamic beauty from free images that are available on the internet. Fantastic. So I'm a great believer in Jade Helioviewer. It's a wonderful program, and everyone who is with us today, give it a try. You'll be very, very impressed at the videos that you can create from it. It's a great heads up, Jade Helioviewer. .05 nanometers. There we are. Yep. Thanks, Kevin. I wanted to be a little bit conservative on this. 0.05 nanometers is not much of a bandpass at all. Hey, Ashley.
Yeah.
So the Doppler effect is going to move that hydrogen alpha wavelength way out of that bandpass. Hence the tuning of these telescopes. Yep.
Oh, very interesting.
Yep.
Now, I don't know how Anne-Marie is going with skies no Lee's battling clouds at the moment. I've got screens all over the place.
Cloud, sorry.
Clouds as well.
Okay.
We might be clouded out for the rest of this now, Russell.
Well, I do have an opportunity to show an animation that I created from Jade Helioviewer.
Yeah, let's do that.
Wanted to do that, so
Yeah.
I will see if I can find it. That's the big if. See if I can find it. That's a big if.
Oh, sun's coming out.
Do you want to grab it, Anne-Marie, whilst you can?
No.
No, okay.
While you're getting yours there, ready there, Russell?
Yep.
We've got a couple more questions. Jamie and Lenny are keeping you on your toes.
Very good.
Jamie
I like
wants to know, in human terms, what is the age of our sun?
Wonderful questions, and this is the beauty of astronomy, actually, everyone, that it confronts us with numbers that are way beyond our comprehension. So the best estimate of the age of the sun is about 4,600 million years. 4,600 million years. And the age of our solar system is just slightly less than that, about 4,500 million years. And so that's, well, they're big numbers. And compare that with the age of our universe, which is believed to be very close to 14,000 million years or 14 billion years. So our solar system is about a third of the age of the universe. About 4,600 million years, or 4.6 billion years. Hard to comprehend. I know during COVID, the last year, it seemed to have taken an eternity, but when you multiply that by 4,600 million, that gives you an idea of how long our sun has been around. And I will add that our sun is expected to be around for about another 4,000 or 5,000 million years before it finally runs out of fuel and becomes a white dwarf.
So that's about the length of the next Victorian lockdown.
Well, hopefully not. Well, I'm hoping that might be the New South Wales lockdown.
Oh, that might be the New South. Okay, yeah.
Because they were making funny remarks, Victorians, when we had our lockdown.
They were.
Anyway.
Let's not be mean to them.
No, that's not me.
Lenny has another question about the quark. Does the Daystar quark need the additional energy rejection filter?
Well, that's an extremely good question. Thank you very much for that. The suppliers of the Daystar quark recommend using an aperture no more than about 4 inches, about 100 millimeters. Otherwise, there's too much energy has to be rejected by the Daystar quark. However, I have put a Daystar quark onto my 5-inch refractor without any issues. So I would nevertheless still stick with the manufacturer's recommendation of using an aperture no more than about 100 millimeters. Now, if you have a refractor larger than that, and I'd be very envious if you did, you can stop the aperture of your refractor down to 4 inches just by putting a cardboard stop over the front of your lens to cut down on the amount of light coming in. And ladies and gentlemen, I want to stress that it is preferable not to use the Daystar quark on a reflecting telescope, that is a telescope that uses mirrors, because the heat of the sun inside the telescope tube can affect the any glues or adhesives that are used, for example, to stick your secondary mirror onto the secondary holder. That heat can loosen the glue and your secondary mirror could fall off. So the Daystar quark is recommended for use with refractors. If you have a reflector, then it would be recommended to stop the aperture down quite a way to maybe 2 inches, just to reduce the amount of energy that gets into your reflector, to minimize the chances of any untoward damage occurring. But as I said, I'd stress the Daystar quark is recommended for refractors, telescopes that use lenses up the front. It is not as well recommended for reflecting telescopes.
I think we've run out of questions, and I don't know how the clouds are looking. I know Lee said that he thinks New South Wales has sent the clouds down.
They did.
They did, yeah. I don't know, Anne-Marie, if you've got clouds still as well?
Coming and going.
Coming and going.
Okay, well, I do have a video that I've created.
Yes, we've got to look at that video, don't we? Yes.
I hope that I can present it.
Right as I get a clear patch.
Have you got a clear patch?
No, it's gone. It heard me say that.
Okay. So I'll show this video using J-Helio Viewer. So this is data or images from the SOHO probe, which is up there in space orbiting. And so you're freely able to collect a number of these still images. J-Helio Viewer will put them into a video, and here we go. And these were about a month during 2003, or crikey, 18 years ago now, when the sun was very, very active and lots of sunspots were visible. So J-Helio Viewer is a wonderful program for creating videos like this, but also images in hydrogen alpha or in the far ultraviolet, showing the beautiful arcs of solar particles traveling around magnetic fields that are coming out of the sun. Absolutely fantastic stuff that you can do yourself using J-Helio Viewer. And that's a wonderful suggestion. Thanks very much for asking that question about J-Helio Viewer. So much wonderful ability available nowadays for amateurs and interested people like ourselves to get fully immersed in solar science or any other science pertaining to astronomy or whatever.
No, Russell, I like how you can see some of these sunspots just appearing out of nowhere.
Correct. Yes. Now, it probably would have taken a day or two for them to appear, because this has taken over about a month or thereabouts. But yes, just gives you an idea of how quickly sunspots can appear. And despite times when there are lots of big sunspots on the sun, here we go, no sunspots during that time, but they're around. I'd like to point out, you can see some lighter patches from time to time. There we go, just around the edge of the sun. These are called faculae, which are slightly hotter regions of the sun, which are easier to view near the edge of the sun because it's slightly darker there.
So,
But our very own style, ladies and gentlemen, and how wonderful it is to be able to study it safely at our own leisure, either through use of solar telescopes or through what is available online through NASA websites.
I've got another question for you from Tim. Does the sun spin in the same way as the Earth and other planets?
Absolutely, Tim, and that's a fabulous question. Yes, the sun rotates from west to east as the planets orbit the sun from west to east, and as the majority of the planets orbit the sun similarly west to east.
And then there's a follow-up from him wanting to know the sunspots, they appear to mainly be on or near the equator. Is this due to the sun spinning?
No, once again, these are fantastic questions. Thanks for that. Now, there's a specific region of latitudes on the sun where sunspots normally appear. And it's something like between about 40 degrees and 40 degrees north and south of the sun's equator, and about 20 degrees north and south. So there are particular latitudes where sunspots appear. And that's very, very well spotted. You know, it's very, very rare, unknown really, to have a sunspot visible near the solar pole down here or up there.
Now,
Good question.
we're going to put you to work, looks like, Russ.
Again?
Lenny wants to know if you can do a tutorial on J Helioviewer one time. So maybe that's something that we can work on.
Absolutely. Absolutely.
Put a video together for everyone to learn how to use it.
And thanks for your interest. That's a great suggestion, Lenny. Thanks very, very much for that. We will certainly do that for one of our presentations. Fantastic. Great.
Lee, have you got clear sky?
Yeah, I think as long as I don't talk too loud, it won't notice.
Okay. I'll stop sharing then, Lee.
Yep.
So if Lee whispers, the clouds won't come.
Yep. So,
Quiet, everyone.
okay.
Quiet, everyone.
Hopefully
There
we
we
should
go.
be seeing that in both.
Woohoo!
We're seeing that in Zoom and on StreamYard.
Okay, good.
Fantastic. So what are we seeing there, Lee?
So it's the same sunspots that Anne-Marie had earlier, but I have a slightly different orientation on my scope, obviously. So these are up the top instead of, I think, Anne-Marie's were down the bottom.
Now, do you have a hydrogen alpha filter on your setup?
No, this is nothing more than it's quite a cheap, so to speak, solar filter,
Right.
which goes on the end of I've got a an 8-inch Edge HD Smith Cassegrain. So
Yep.
this actually, it looks exactly like the cover for the OTA itself, the scope itself. Oh, look, there we go. There comes the
Woohoo!
yeah.
Anyway, so this,
Justin,
Lee, for
timing was
clarification, one of
impeccable.
the shiny metallized film filters that
Correct.
goes over the front.
Yeah,
Yeah.
so it's actually it looks like they've really, part of what the Celestron have done is they've got those the covers for the scope, but then they've just also manufactured the same cover with holes cut out of them and the solar film plastered in them. So it's obviously considerably, I think it's considerably cheaper
Absolutely, mate.
than
Yes.
the method that against the Quark, but
Yeah.
it's just
But it's
coming out.
a very cheap and cost-effective way of at least viewing sunspots.
Absolutely,
sun.
yeah.
So these filters, we call them white light filters because they let all of the sun's every wavelength of the light through, rather than just allowing a specific wavelength through, like the hydrogen alpha filters do. So sunspots show up very, very nicely in white light filtered arrangements, and you can use your reflecting telescope like you're doing, or a refracting telescope, as long as it has this white light filter over the front of the telescope, and a wonderful way to observe sunspots. Fantastic. Just a point of clarification though, with the white light filter, you're not going to be able to see prominences around the edge. You're not going to see the beautiful wavy structures that we saw in hydrogen alpha. But nevertheless, you can see sunspots, and you may see some granulation on the sun as well, which are these hot and cold zones.
Yeah,
Gas rising up and cooler gas rising down.
I could
So
see
it's
that
fantastic.
slightly when it was certainly a lot clearer earlier, and just sort of rolling through different changes in the gamma and brightness, which I wouldn't
Yes.
normally do, in doing DSO, deep space objects.
Sure.
I don't normally touch that much, but
Yep.
yeah, certainly changing those. I could even see that there's these 2 extra spots
Exactly.
just up
Yes.
the top.
Yep. As a means of increasing contrast.
Yeah.
Yes. And ladies and gentlemen, can you see that the sunspots have got a black center and a slightly grayer outer region? So the black region is called the umbra, and the slightly grayer region around that is called the penumbra. So sunspots are not uniformly black. There's a black center and a slightly grayer periphery.
Oops, changed my contrast the wrong way.
Fantastic.
Yeah, so I can probably stop sharing that one, and we'll
Thanks very much, Lee. And so we've seen views through the 2 most interesting ways of viewing the sun, through hydrogen alpha and through white light filters. So fantastic. Now I think, folks, we will, if you don't mind, Mark, we'll call this.
Yes, I know astrophotography need to jump into Zoom soon, don't they?
They will.
They will. So
may I just finish off by thanking everyone for viewing our solar demonstration today. I hope you found it of interest and informative. And so please be mindful that we will be holding these sessions in the future. So keep an eye out for them and join us and enjoy some rare views of our very own star, the sun. So thank you very much and have a good day.
awesome. Thank you.